Hello. We begin our discussion of discrete mathematics. We're in our first lecture. I want to welcome you all. We're going to begin our discussion talking about logic, and there are lots of different logics to talk about. Your book devotes two chapters to it. Chapter 2 is called The Logic of Compound Statements. Chapter 3 is called The Logic of Quantified Statements. These are the two chapters we're going to begin this class with, and this is going to be very important material as we'll be using logic throughout the rest of the class. Let's try and distinguish what we mean between the logic of compound statements and the logic of quantified statements. Now, suppose I were to make the following statement. Suppose I were to say to you that today is Tuesday. And what we're going to do is we're going to take this entire statement and we're going to assign it to a variable. So we'll call the variable A. So the interpretation here is that if I write down the symbol A, I'm referring to the statement that today is Tuesday. Now, this particular statement, we can say one of two things about it. This statement is either true or false. So we can come over here and we can make a truth table, and we can just say A, and this is a very simple truth table. It's either false or it's true. Okay, now I want to compare that with a different kind of statement over here. Suppose I were to come over here and say something like apples are red. Now, this is actually a very different sort of statement, and it's actually a much more powerful statement because what I'm saying over here is I am saying that for all the objects in the universe, if the object is an apple, then the object is red. So this is making a statement about many, many, many things, okay? This is making a statement just about a single thing. And this is primarily the difference between what is occurring in chapter 2 and what's occurring in chapter 3. This over here is sometimes what is referred to as a proposition. Okay, and what we're actually studying in chapter 2 is what is called the propositional logic. Okay, this statement over here, apples are red, this has a very fancy name in mathematics. This is what's referred to as we are speaking in the first order predicate calculus. Wow, big words here. And this is occasionally abbreviated this way. So the key words that you should pick up here, in chapter 2, we are talking about what are called propositions. In chapter 3, we are going to be talking about things called predicates. And that is what distinguishes the differences between these two chapters, both important concepts, and we will be exploring them further. Okay, so let's go back to our sentence here. Sentence A, and we will say that sentence A, again, represents the statement that today is Tuesday. And let's introduce another sentence. Sentence B. My name is Joe. Okay, now One of the things that we're going to be doing in this chapter is we're going to be taking simple statements like this and we're going to be combining them. There are different operations that we can perform on them. The first one is very, very simple, and I'm sure you're familiar with it. It's called negation. And the symbol for negation is this little squiggly symbol there. So we might do something like this. We might say that, and we would read this squiggly line here as the word not, okay? And again, what we can do here is we can make a truth table, and we come over here and we can say A, and we can come over here and then we can talk about not A. And basically we could say that if A is false, then not A would be true. And we can say that if A is true, then not A would be false. And I think that that coincides with what we think it should be. Now, we have a couple of other operations that we want to talk about how we can combine these two sentences into a bigger sentence. And one of them is what is called or. Okay, and that is sometimes another big fancy word for or is the word disjunction. I do not believe they use this term in your book. And the symbol for this is, it looks like a little V. And what we can do here is we could write the symbol A or B. And again, at least given these two symbols right here, the interpretation of this statement right here would be today is Tuesday or my name is Joe. And we can come over here and we can make a truth table for that. And now I have an A and I have a B. And I can talk about A or B. And the question we need to ask ourselves is when do we think that A or B is true, or when do we think A or B is false? Well, I think our normal understanding of the word or is that it must mean that at least one of these is true. So, for example, if today is Wednesday and my name is Joe, then to say today is Tuesday or my name is Joe would be a true statement. In fact, if you think about it, the only time that this statement over here is going to be false is when both A and B are both false. If today is Wednesday and my name is Sam, then I think you would agree that this statement over here would be false. So if I want to draw a truth table to indicate how this statement actually works, the first job that I have is I have to consider every combination of trues and falses over here. And I think you can see that if I have two symbols over here, there are going to be a total of 4 different ways to consider this. So I could consider the situation where both of these are false, or I could consider the situation where A is false and B is true, or I can flip those around and I could have true and false, or I could come over here and I could have true and true. And by the discussion that we just had over here, I think you would agree that the only time that this statement is false is when both of them are false. So this over here represents the truth table that we have for the logical operator or logical connector called OR, which is using this symbol right over here. Okay, moving along, again, we have this statement A, and now I want to consider a different logical connector, that upside down symbol right over here. This is sometimes what is called AND. Another fancy word for this is this would be referred to as conjunction. Again, we go ahead and we make the truth table for this. So again, with two symbols over here, we note that there are four possibilities. A and B. And we note the following. If I were to say to you, today is Tuesday and my name is Joe, we know that that is a true statement only in the situation where both of these are true. Otherwise, it's false. So again, I come over here and I say false, 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 true, true, false, true, true. And we know that in this situation it's true, but in every other situation it's false. So this is a pretty straightforward procedure here, constructing these truth tables. Suppose I were to say to you something like the following. Construct a truth table let's make it a little bit more complicated. And I were to come over here and I were to say A or not B and C. Now we've done something new here. I've used parentheses, and you should think about the parentheses the same way you did from your algebra class. What I'm saying over here is that in evaluating this particular proposition, we should do this operation first. And I want to create a truth table for this. But now I want you to notice that now I have three variables. And what I need to do here is I need to consider all of the possibilities of assigning A, B, and C, either the values true or false. So first thing, I want to think about how big is this truth table going to be? Well, for every one of the two values that I can assign C, I can assign this two values, true or false. And I can assign this two values, true or false. And I can assign this two values, true or false. So the total number of ways that I can assign all of these different values of true and false would be 2 times 2 times 2. So that means that there are 8 different ways that I can assign these values true and false. And what I'm going to do over here is I'm going to do something like the following. So I come over here, here's A, here's B, and here's C. And this is going to be a bigger truth table. And I consider all of the different ways that I can do this. And I hope I have enough room here. True, false, true. It looks like I'm going to make it. I have to print very small. There we go. So we can see that there's 1, 2, 3, 4, 5, 6, 7, 8 different ways that I can assign these three variables different values of true and false. And in fact, I think you can see, you should think about this, a good homework assignment. If I have x variables, then the truth table is going to be 2 to the x rows. So in other words, if I had 4 variables here, my truth table would have 16 rows in it. If I had 5 variables in here, the table's getting really big, it would have 32 in it. But what I'm going to do over here, okay, so I've got A, B, and C, and now I want to figure out, with these various values of trues and falses, what is the value of this? Okay, so we can think about this as follows. First of all, if I come over here, let's do it this way. We'll break it up into pieces. First, I'm going to look at A or not B. And then we'll come over here and we'll look at C. And then we will look at A or not B and C. Okay, so let's consider A or not B. Now we know that this is true if either A is true or not B is true. So first of all, if this expression here is true whenever A is true, well, A is true in these four cases right over here. So I certainly know that this is true here, and it's true here, and it's true here, and it's true here. Now, this expression is also true whenever not B is true. Well, not B will be true whenever B is false. So in these remaining four cases here, well, I see B is false over here and over here. So what's going to happen is this is true here, and it's true over here, but in these two cases here, it's false. Now over here for C, I just have to repeat this column right over here, and we can see it's false, true, false, true, false, true, false, true. So I'm going to come over here and I'm going to say false, true, false, true, false, true, false, and true. And now what I'm doing in this very last column is I'm taking the AND of this side and this side. So let us recall that when we're using AND is true only when both sides are true. So I'm going to get a true in this column wherever I have trues in both of these columns. So there's a true right over there. And there is a true right over there. And there is a true right over there. Everything else is false. So let's imagine that somebody were to say to you, under what situation is this statement over here true? And you would say, well, it's true in this situation right here, and it's true in this situation right here, and it's also true in this situation right here. Otherwise, it's false. Very frequently, logical statements can get very complicated, but with a little bit of work, you can show that they are equivalent to something that is much, much simpler. So we need to explore how do we show when two logical statements are actually equivalent to each other. So here's the example that I want to work with over here. I want to talk about the following statement. I want to say not A or B. And I want to claim that that is equivalent. And here's the symbol that I'll use to mean equivalent. Almost looks like an equal sign. And I wanted to show that that is actually equivalent to not A and not B. So first of all, let's just take a look at what we've done here. It almost looks like I've taken this not sign and I've distributed it over the A and the B. And then what I've done is I flipped this around. I made an OR into an AND. So let's come over here and do the following. Let's talk about A, B, And we're going to do this in a very long way just to make everything obvious to you. So I'm going to come over here and I'm going to talk about, well, what would A or B be? And then I'm going to talk about what is not A or B. And then I'm going to come over here and I'm going to say, let's look at not A. Let's look at not B. And let's look at not A and not B. And let's draw our columns. Now there aren't going to be too many rows to this. I'm just dealing with two variables. So there are going to be 4 rows to this. So I'm going to come over here and just fill in the rows, false and false, false and true. Okay, so A or B is easy. The only time that that would be false is right over here. Otherwise, it's true. And now over here, I have not A or B. So I'm just going to take this column right here, and I'm going to flip it. So this becomes true, false, false, and false. Okay, so this over here, along with A and B, becomes the truth table for this expression right over here. Now we have to figure out the right side. So first of all, I have not A. Well, not A is just going to flip this column over here, the A column. So I'm going to get true, true, false, false. And now I'm going to flip the B column over here. So the false becomes a true, and the true becomes a false, and this is a true, false. And now what I'm doing over here is I am ANDing them. I'm ANDing not A and not B. So we recall that AND is true only when both of these are true. So I come over here and I see, well, they're both true right over there. And in these 3 cases here, they're going to be false. And now this column represents the truth table for this. Now, here's the important thing to notice. Come over here and look at this column and compare it to this column. And we note that they are exactly the same. This one here, and then this one here. So what we have demonstrated here is that this expression right over here is logically equivalent to this expression right over here. And this is actually a very, very important logical equivalence, so important that it has a name and you should probably commit it to memory. This is what's referred to as De Morgan's rule. And there are actually 2 forms of De Morgan's rule. In this case over here, we have taken a not and we're distributing it over an or. The other form of De Morgan's rule looks like this. It says that not A and B is equivalent to not A. And again, then what we do here is we flip the and becomes an or, not B. And that is a not. Okay, so this is De Morgan's rule, and this is De Morgan's rule. And I ask you as a homework exercise to draw up the truth table for this and verify that they're logically equivalent. Remember, what happens is if we are trying to show the two expressions are logically equivalent, and we go ahead and we come up with the truth table for them, and there is a place where these don't match, then what we have shown is that the expressions are not logically equivalent. Some help here on constructing truth tables. If you found a little bit confusing, maybe this will help a little bit. I want to suppose that I were asked to construct a truth table for something, let's make it complicated. We're not going to construct the entire truth table, but I think you'll get the idea. Suppose I were asked, whoops, already made a mistake here. So let's come back here. Now the whole thing is a mess. Okay. A and not B or C and not D. So the thing to notice here is that we have four variables here, A, B, C, and D. And each one of these can assume the value true or false. Now, very frequently, it's sometimes easy to think of 0 as being false and thinking of 1 as being true. So let's come over here and think about a couple of things. First of all, let's look at the value D. Now, the value D can either take the value 0 or 1. Okay, so there are a total of two values that it can take. Now let's introduce the variable C. Well, C can take the value 0, or C can take the value 1. Now, when C takes the value 0, then D could be 0 or D could be 1. Or when C takes the value 1, we could have D taking the value 0 or D taking the value 1. So if I were just talking about C and D now, I could have C being 0 and D being 0, or C being 0 and D being 1. So that would be 0, 0, or 0, 1. Or I could come over here and C could be 1 and then D could be 0. So that would be 1, 0. And C could be 1 and D could be 1. So that would be 1, 1. So with just these two values here, okay, I can either have a 0, 0, 0, 1, 1, 0, or 1, 1. And for those of us that speak binary, and I think everybody here does, you'll notice something going on here. I actually have a binary 0. Here I have a binary 1. Here I have a binary 2. Here I have a binary 3. And notice that with two variables here, I have a total of 4 different combinations. Now, if I were to come over here and introduce the variable B, B could be 0. And then I could come over here. Or B could be 1. And if B is 1, notice what I have to do is for this situation down here, I have to take this whole picture right here and I have to move it down here. So I could come over here, B is 1, and then I could come over here and I could say that C could be 0, or C could be 1. And then over here, I could say that D is 0, or D is equal to 1. Likewise, when C has the value 1, I come down here, and D could be 0, or D could be 1. So now, if I come over here and follow this all the way through, I could have B being 0, C being 0, and D being 0. That would be 0, 0, 0. I could come over here and B could be 0, C could be 0, and D could be 1. And I think you can see the pattern. What's going to happen now, if I follow this all the way through, the very last one over here, B would be 1, C would be 1, and D would be 1. The last thing I would get down here is 1, 1, and 1. So now, if I'm counting in binary, you can see that I'm going all the way from 0 up to 1, 1, 1. 1, 1, 1 in binary would be 4 plus 2 plus 1. This would be 7. I'm counting from 0 to 7. So that now, and I'm not going to draw it because the tree is going to get very large, but I would come over here and I could talk about A being 0 and take me up to there. I could come over here and A being 1, and then what I would do is I would take this whole thing and repeat it down here. And you can see what's going to happen over here as I follow each one of the paths from A all the way through to the various values for D. I'm going to get and right down here, the last pair here is going to look like this. And we can see that I've gone from 0 all the way up to 15, okay, for a total number of 16 possibilities. So we can make a rule here. If I have n variables, okay, then I will have 2 to the n rows. And you could think of these rows as being numbered, and they go from 0 up to 2 to the n minus 1. There are two important definitions that we should be aware of here. One is what's called a tautology. And that's already spelled incorrectly. My apologies. Tautology. And you can think of a tautology as something that is always true. The other one's what's called a contradiction. And a contradiction means always false. So let's give a couple of definitions of these. There are actually two very famous ones. A tautology would be P or not P. Okay, we note that regardless of what the value of P is, this statement's always true. If P is true, then I have true or false. That's a true statement. If P is false, then I have false or true, and that is always a true statement as well. Okay? So this is a statement over here that is always, always true. It doesn't matter what value I assign to P. So let's give an example of something that's a contradiction here, and that's pretty easy to do as well. If I were to say P and not P. Now remember, for an and to be true, it has to be the case that both of these are true. But we see that that can't be the case. If P is true, then not P is false, and true and false would be false. Likewise, if P is false, okay, then this would be, if P is false, then this would be false and true. And again, that would also be false. So tautology, contradiction. Sometimes if you look very closely in an expression, you might see a tautology or a contradiction hiding in there, and you can tell whether the entire statement is true or not. Let's consider something like the following. Suppose I were to say to you A and not A, and B or C and not D or F. F is a bad choice of letters here because that could stand for false, so let's make this G. So suppose somebody gave you this expression right over here, and they were to say to you, make a truth table for it. Well, if you're clever, you can look at this and you can go, well, I really don't have to make a truth table for it. First of all, if this is going to be true, notice that I am anding something. I'm actually anding three different expressions here. And if this entire thing is going to be true, it has to be the case that this has to be true, this has to be true, and this has to be true. But I come over here and I look at this and I notice that this is a contradiction. This expression over here is never going to be true. Okay, so that means this is always false no matter what the values of A, B, C, D, and G are. So if this is always going to be false, that means that this entire expression over here is always going to be false. I don't need to go ahead and make my truth table here. Okay. On the other hand, if I were to come over here and say something like the following, A or not A, or okay, again, notice I have an expression over here that has 1, 2, 3, 4, 5 different terms in it. If I were to make a truth table out of this, it would have 2 to the 5th rows in it, 32 rows. That's pretty big. But notice what I'm doing over here is I'm ORing a bunch of things together. This statement, the entire statement, is true as long as one of these three sub-expressions is true. And I notice over here, I have a tautology. A or not A is always true. So it doesn't matter what the values of A, B, C, G, and H are. This expression over here is always true. Okay, so what we've done here is we have used tautology and contradiction to help us a little bit in our work, that we don't have to go ahead and build these tremendous truth tables over here. Now, this leads to one more thing that is mentioned in the book. The book gives a bunch of what are called logical equivalences, and we've already talked about what logical equivalences are. And there are quite a few of them. I'm not going to go through all of them here, but these are something that you should all be familiar with. So I invite you all to look at Theorem 2.1 in your book. Theorem 2.1 in your book, and in my copy of the book, it is on page 35. But you'll see statements in there. Some of them are kind of obvious. For example, P or Q is equivalent to Q or P. Okay, this is sometimes referred to as the commutative law for OR. You may recall that the word commutative, you learned that in algebra. Multiplication is commutative, like A times B is equal to B times A. So that's a pretty easy one. Some of the ones that are a little bit hard to remember are these various associative rules. For example, you have P and Q or R. That is equivalent to P and Q. Or P and R. Okay, that's an example of the associative rule. And as a homework assignment, You should absolutely look over these logical equivalences, Theorem 2.1, page 35. You should know them all. Most of them are going to seem very, very obvious to you, and these things are very, very helpful in assisting you in taking complicated logical expressions and making them into easier ones.